Hello, welcome back. Today we're going to talk about moments. To introduce the concept about what moments are, I want you guys to see a very short video about 3 minutes where this guy explains to us what is this new concept about moments. Let's take a look.
In this session, we are going to talk about rigid bodies and moments. We earlier discussed about forces. We used the equation sum of all the forces equal to 0 in solving static equilibrium problems. This approach worked very well for particle equilibrium problems. As you recall, a particle is a concentrated mass. Shape and size of an object is ignored when we consider that object as a particle. Particle is typically represented as a dot, so there is no rotation. However, this approach won't work when we deal with the analysis of bodies for which we cannot ignore their dimensions. In other words, we can't use the particle assumption all the time. If we want to analyze a body in detail, we have to consider its shape and size. We are going to assume such bodies as rigid bodies. A body that does not change its dimension under the action of forces is a rigid body. Since rigid body has actual dimension, we cannot ignore the rotation. Rotation relates to moment. So let's talk about moment. We use the word moment in our everyday life. We use it often to indicate an interval in time. There is even a great song, one of my favorites, by Whitney Houston. I want one moment in time. However, in the context of engineering, moment is very different. Moment can be considered as a rotational force. Let me explain. We know force is a push or a pull. But force alone is not enough to do our daily work. Think about driving. We have to rotate the steering wheel. Think about pulleys. In all these cases, we have to deal with rotational motion. How do we create rotational motion? It can be done using a force, a push, or a pull. Let me start with an example. Here I have a wrench. A wrench is used for tightening a bolt or loosening a nut. Let me hold the wrench like this. If I want to use it, I have to apply a force somewhere here on the handle. This force is a push applied at a distance from the center of rotation. This push creates what I call the tendency of the force to rotate the body about an axis that passes through the center. So, moment is a tendency of a force to rotate an object about an axis. The magnitude of the moment is equal to force times the perpendicular distance from the line of action of the force to the center of the rotation. Hence, the unit for moment is going to involve the unit for force and distance. Unit for moment is Newton meter in SI system. Unit for moment is pound foot in US customary system. What we are going to do now is learn how to calculate the moment of a force in two-dimensional plane with some examples.
First example, very simple. We have a point, let's call it point A, and we have a force. Let's give some dimensions. From here to here we have 3 meters, and let's say this force is 4 newtons. So if I draw a line from the point to the line of action of the force, it will be this line here, and if this is 90 degrees, this will be the distance, 3 meters, from the point to the line of action of the force. That's the distance that we need in order to calculate the moment. Because we heard the guy said moment is equal to force times distance, where distance is perpendicular to the line of action of the force. So the moment here is going to be 4 newtons times 3 meters, 12 newton meter. Easy enough. Okay, that's it. Well, let's take a look at some elaborated examples. Let's say the force is not exactly in front of the point. Let's say we have here our point A and we have a force here. Force. Okay, we have to establish the line of action of the force. So it's this straight line from which the force is a segment. That's the line of action. Line of action. And then we have to define the distance. Well, we may have this distance here. That's not the distance that we can use to calculate the moment. The distance has to be perpendicular to the line of action, perpendicular like this. This has to be 90 degrees, so this is D. So if this force now is 10 newtons, and this distance is now 5 meters, then the moment here is going to be 10 newtons times 5 meters. The moment is going to be to 50 newtons meters. So if we don't have this distance perpendicular to the force, we cannot calculate the moment. If we have this one right here, let's call it D1 or D2. If we have this one here, if this is the distance that we have to find a way to obtain the perpendicular distance. For example, we might have the angle here. If we have the angle here, let's say this is 40 degrees. Then we can calculate this one here. Let's try a different example. Let's say we have here our point A. We have a force going up like this, and we have this point B here, and we have this distance here. Let's say D equals 5 meters. And then if we want to calculate the moment of this force, let's say this force is 20 pounds, 20 newtons. If we want to calculate the moment of the force with respect to point A, well, we cannot do it because we don't have enough information here. Only if somebody tells us that this is the line of action of the force, and we can find the perpendicular distance from that line of action, from that point A to the line of action of the force, where this is 90 degrees. If somehow we find the information that this is 30 degrees, then we can find this distance. Let's call it D perpendicular. D perpendicular to the line of action will be 5 meters cosine 30 degrees. So that distance will be 5 times 0.666, right? 5 times. So that will be 5 times cosine of 30, 4.33 meters. So now we can calculate the moment as 20 newtons times 4.33 meters. Times 20. So the moment will be 86.6 newtons meters. All right. Another problem. Let's say we have this construction here. Point A, point B. The force of 10 pounds makes 75 degrees with the horizontal. And the distance from A to B, the line from A to B forms 40 degrees with the horizontal. We need to calculate the moment of the force F with respect to point A. Okay, we don't have the distance that is perpendicular to the line of action, so we have to find it. So let's make a construction here. We draw the line of action of the force. The line of action of the force will be this line here. Let's put it here in red. That's the line of action of the force, right? And we need to get the distance from point A perpendicular to the line of action. So we need to draw a line that is perpendicular to that red line, coming down from point A. That distance, that will be the distance D that we need in order to find the moment. That's the distance that is perpendicular. This angle is 90 degrees. Okay, what is that distance? If we have this angle here, let's call it alpha for now. If we get this angle alpha, then 40 plus alpha will be the angle that we can use in order to multiply 15 feet. Cosine of this beta will give us the D. This distance will be equals to DAB cosine beta. So what is this angle alpha? If we draw parallel to this green line on the point B, this other green line here perpendicular to the force, so this angle is 90 degrees. This is 90 degrees. So then this is alpha. 90 minus 75, this will be 15 degrees. So alpha will be 15 degrees. So therefore, D is equals to DAB cosine of 55 degrees so that will be equals to 15 cosine of 55 degrees. So the moment will be equal to 10 pounds times 15 feet cosine of 55 degrees. So this moment will be equal to 86 pound-foot. That will be the way to find that moment in the case that we don't have the distance that is perpendicular from the point A to the force F, or to the line of action of the force F. All right. Sometimes it's well, it's not like the ideal case, but it's doable. But we can make use of a tool that is called the Varignon theorem that tells that the moment of a force with respect to a point is equal to the summation of moments of all the components of that force with respect to the same point. I repeat, the moment of a force with respect to a point is equal to the summation of the moments of the components of the force with respect to that point. So let's make the same example by using that theorem. I erased some of the elements of the previous way to develop this moment in order to do it now using components of the force. I left the answer here so we can check if we got the same answer. Let's put it here on a corner. This is the answer that we got. So now we're going to take the components of this force. One component in the direction of the line that goes from A to B, and another component perpendicular to that direction. So what I'm saying is I have the line from A to B, this line, and if I continue that line, right, and then I make a perpendicular line to a line perpendicular to AB, that will be this one right here, and I take the components of the force, this is point B, the components of the force along the direction of those lines. Let's put it here in blue, very thick blue. So do I have this component here, even thicker, maybe better, this component right here, and this component right here. You see here I get to make the force F, I get the components of force F in the direction of the line AB in the direction perpendicular to the line AB. Let's call this one F normal, and let's call this one F parallel. You see what I did right there? This is F normal, is a line that is normal or perpendicular to AB, and this FP is in the direction of AB or parallel to AB. We know that, let me increase the size here so we can see 1 second what are the angles here. So we have 75 degrees is the angle from the force F to the horizontal. Now we need to get this angle right here, this angle right here. Okay, what is that angle right here? Let's make it very big so we can see it. This angle is 40 degrees. We got it from here, 40 degrees, right? So, and if the total angle from the force to the horizontal is 75 degrees, then the angle that we need here is 35 degrees, right? Let's see what angle I'm talking about. So I'm gonna do it a little cleaner here. Let's remove the force from here. So here the force of 10 pounds, and now we have this angle 75, this one 40, this one 35. So if we want the components of the force F, will be Fp equals to F cosine 35, and F normal equals F sine 35. All right. So now let's calculate the moments of those two forces. Those two forces, Fp and Fn, are the components of force F. The moment of force F with respect to A, we found it to be, remember we had it here on the corner, 86 pounds-feet. Now we're going to calculate it. We're going to calculate it based on the components. The moment of force Fp with respect to A is equal to Fp multiplied by the distance from the point A to the line of action of Fp. If you see, point A is sitting on the line of action of Fp, this line right here. So the distance from that point to that line is 0. So that's a big 0 here. So the moment of Fp with respect to A is 0. Now, the component Fn, let's calculate the moment with respect to 8 of the force Fn. Fn times the distance perpendicular from A to the line of action of Fn. That will be point A again to the line of action of Fn. That will be this line here. Because the construction that we made, this angle is 90 degrees, right? Because we made Fn perpendicular to AB. So that angle is 90 degrees. So in order to calculate the moment of Fn with respect to A, we have the force Fn already here multiplied by the distance measured perpendicular from point A to the line of action of Fn, which is this 15 feet. 15 feet. And what is Fn? Fn, we had it from here, is F multiplied by sine of 35 degrees. That's Fn here, multiplied by 15 inches, multiplied by, 15 feet. So that comes to be equal to F is 10 pounds, sine of 35 degrees is 0.57358 times 15. This is equal to times 15 and 10, 86.04. 86.0 pound feet. Okay, so and the summation of actually I should put it like this. The moment that we just calculated, we calculated based on the moment produced by the components, which is this one plus this one. That summation is equal to this value because this plus 0 is this. So this is equal to the moment that we calculated before, that was based on calculating the moment as the multiplication between the force and the distance perpendicular from the point to the line of action of the force. So I hope you guys saw, so you guys see what we just did here. We first calculate the moment as force times distance perpendicular to line of action. And then this new version here is the moment calculated as the summation of two components, the moment produced by two components, one perpendicular to the line AB and another parallel to the line AB. One of those components doesn't produce any moment, so that's the 0 that we have right here. So the total moment is produced by the other component, Fn, and we got the exact same value. All right. We can do now another different composition of the force F, and we apply the same Varignon theorem to see the validity of the theorem and how it's very useful for calculation like this. Let's make the same construction again. Okay, we have the same initial problem again, but now I am going to get the composition of the force in these two new components, vertical, let's call it Fy, and horizontal, Fx. And now we are going to calculate the moment of F with respect to A as the summation of the moments produced by its components Fx and Fy. So that will be, initially we did it as F times D, dAB, right? Okay, now let's see the components. Fx is equals to F cosine 75 and F Fy is equals to F sine 75. Now we need to find the distance from point A to those two forces, perpendicular to those two forces. If I make a projection of those lines, of those forces, I have the line of action of x, f, y will be this distance here, this line here. And this horizontal here will be the line of action of fx. So in order to calculate the moment of fx, the moment of fx with respect to A, that's too thick, will be equals to fx times this distance here. I'm gonna call it dy, right? Dy will be equal to dy will be equal to dab sine 40. So I have fx is f cosine 75 times dy, which is dab sine 40. So this moment will be f, which is 10 cosine 75 times dab, which is 15 sine 40. So that moment will be 24.955. Now the moment of Fy with respect to A is going to be equal to Fy times the distance from A to the line of action of Fy, which is this horizontal line here. We can call that distance dx, and dx is now Fy is f sine 75. Yeah, we got it from here. And dx is dab cosine 40. So that will be 10 sine 75 times 15 cosine 40. That's going to be 10 times sine 75 times 15 times cosine 40. $110.99. Okay. So now we need to find the summation of these two moments in order to find the total moment of A with respect to the force F with respect to the point A. So the summation of moments is going to be equal to this, the summation of these two moments. Now there comes the problem of signs. If we take a look at the moment that the force F produced with respect to point A, remember at the beginning of the discussion today when we saw the short video, we discussed about, the guy talked about some kind of rotation. The moment is rotation, some kind of concept of rotation of the force produced with respect to a point. If you think about this force trying to make point A rotate, is going to, it's going in this direction, is going to try to make a rotation in this direction, right? Now, if we talk about the rotation produced by the components, the component Fy is going up, it's going to produce a rotation kind of in the same direction as force F, so kind of like in this direction. But we look at the force Fx. Fx goes like this, and with respect to A, it produces some kind of rotation in the opposite direction, right? Like this. So we want to find the summation of these two moments. The moment produced by Fy and the one produced by Fx, they go in opposite directions. So I have to subtract one from the other. They don't have the same sign. And we can set up like a convention of signs where we say positive counterclockwise or positive clockwise, doesn't matter. But in this case, we know that there is one moment in this direction, the moment Fy is in this direction, and the moment Fx is in the opposite direction. So the resultant is going to be in the direction of the one that is larger. The one that is larger is Fy. So let's put that one first, 110.99, and let's subtract the other one, 25.955. So we have this one in the counterclockwise direction, and this one in the clockwise direction. So we have, as a result, a moment in the counterclockwise direction that is going to be 110 minus 24.955, 86.0 in the direction counterclockwise. As you see, it's the same value that we found here in the previous cases. So as we can see here that the Varignon theorem holds, you can find the moment of a force with respect to a point by getting the components of the force and finding the moments of those forces with respect to the moment and make the summation. In the previous case, the composition was very simple because one of the components was producing 0 moment. So the total moment was just the moment of the remaining component. And in this case, we have two components that produce rotation in different directions. So in order to get the summation of those moments, we have to take good care of the direction. We found that one of the components produce moment counterclockwise and the other clockwise. So we have to subtract both in order to get the summation. And we see that the winner is the moment produced by Fy that produces a moment counterclockwise. So we have to subtract the clockwise moment in order to get the final result, 86 pounds-feet. So this is another concept that is very important. The moment have direction. Well, like the forces have also direction. Actually, the moments are vectors. We are going to treat to consider in this class only moments produced by forces in the x y in the 2D space. So in this case, let's say this is the xy plane. The moment is a vector in the plane in the direction perpendicular to the plane of that contains the force and the point, and it's going in the direction given by the right hand rule, the right hand rule. So let me try to make a drawing here in order to show the direction of the moment vectors. We won't be dealing much with that. We just clockwise and counterclockwise direction will be enough for us. But let's do this discussion real quick here. So let's say we have here the xy plane. If we have a point, let's say point A here, and a force here that goes from, let's say, this point here to this other point here. This is the force here, F, and we are calculating the moment that this force makes with respect to point A. This will be the distance d. If we look at the rotation of that the force F is trying to produce with respect to the point A, that will be in this direction, in this drawing here. So if you point to that rotation with all your fingers of the right hand, then the direction of the moment will be given by your thumb. So in this case, this will be the vector moment. This will be the moment, the vector moment F times D. Well, actually, this is just the magnitude. F times D is the magnitude. But if you see the moment as a vector, it will be a moment, in this case, going up in the C direction, in the direction of the axis Z. If you have a moment that is produced, say, a force in the other direction, let's put it here in purple here. If I have this purple moment kind of parallel to that one that I drew first time, this one will produce a moment in the opposite direction here. So that will be a moment going down in the minus C direction. There will be a moment going down like this. The rotation is in this direction, goes down like that. So that's another consideration that we have to do about moments. Moments have direction, or we talking about the plane. Moments will go clockwise or counterclockwise, and that's enough for our calculations in this class here. We only work with forces in the 2D plane in order to calculate moments. So now let's do some more examples. We just have to do examples in order to master this how to calculate moments of force with respect to points.